Hi, my name is Satananda. I'm from Marvell. I've been working on Marvell NICs and DPUs for quite some time now. This talk is about realizing composable infrastructure through DPUs. Thank you for attending this talk. So I have been helped by my colleagues Radhamohan and Veerasena in preparing this deck. Just want to recognize that. So first question, what is composable infrastructure? Generally, composable infrastructure is the ability to assign, reassign hardware resources to fit whatever workload you are running. This also means that you have to be able to pool the resources like compute, DRAM, network, storage in other accelerators that you might have in the across the rack or a pod scale and combine them in the right quantities and combine them on demand for running your workload. So this helps in reducing over and under provisioning, and then it also saves you like TCO. For this to be realized, you need to have the right hardware and software architecture for getting composable infrastructure, making it a reality. So there are levels to composable infrastructure. There is bare metal, there is VM, there is container. We'll first go through the bare metal scenario. So you would have your rack or a pod, and your compute can be pulled now at a rack or the pod scale. Memory already is being served by CXL pooling. Network, NIC and GPUs are latency sensitive, so they get tied to the local, to the CPU. There needs to be more work here to get these to be pooled at least rack scale. So today what we got is an ability to choose fixed combinations of resources and some dynamic combinations of resources that you can do at a rack or pod scale. There are multiple vendor products available in the market today with this kind of infrastructure. Now, once you have your server up and ready, now you want to run VMs on your server. How do you compose your VM? Now, so taking an open example with OpenStack, you would have your VMs provisioned by OpenStack's Neutron to provide you some kind of composability where you can assign the VFs of the PCI devices that you are looking for, and you can adjust some of the capabilities and capacities using like something like bandwidth rate limiting and such, using Neutron API. OpenStack is also coming up with Cyborg API, which is a newer addition to manage the complex accelerators that are coming up in the market. The next is containers. Containers are lighter weight, and they are also served by the same kind of technology, like SRIOV VFs can be assigned to containers. The difference here is that the biggest orchestration framework out there, Kubernetes, does provide a flexibility to vendors to manage their own devices using a vendor-defined API, like vendor plugins. These are called container device interface and dynamic resource allocator. So these help the vendors decide how they choose to partition their devices, whether they support SRIOV or not, whether they have their own proprietary mechanism that can be hidden, and vendors can provide devices that can be composed to the Kubernetes environment. So coming to what's missing. So what's missing is we just saw the different ways of doing composability at different levels. And then there are different frameworks, OpenStack, Kubernetes, CDI, DRA, and Redfish, and such. And there is no uniform way of assigning resources to nodes, and then there is no uniform way of prescribing the features of the device that you're looking at. So this results in the rigid assignment of resources, static capacity and capability, and you cannot adjust it during the runtime of the machine or the VM or the container. So some of the questions that come to mind while trying to answer this is, let's say you have a VF, a network VF you are assigning to a VM or a container. We all know network VFs are used to do flow rules. You can offload them. But can you control the number of flow rules that your network VF will support before assigning that to a tenant or a container or a VM? Similarly, you do crypto offload with your network device. Can you control how many IPsec contexts, how many TLS contexts, what's the symmetric crypto versus asymmetric capacity before you provide that VF to your workload? So similarly for NVMe, can you control the number of queue pairs, number of namespaces and such? So these are the kind of questions we are trying to answer when we are trying to come up with a composable infrastructure using DPUs. So first we'll go into what kind of support is needed from hardware for composable devices. So what we need is, like as we just said, all hardware is made up of some granulated or atomic hardware blocks or instances that can be combined into higher order devices, which are your PFs, VFs, or SFs. These devices, these atomic devices, we should be able to assign them, to pool them among your PFs and VFs and such, and that ability should be exposed through some standard framework so that every orchestrator can take advantage of that. For instance, to compose PFs and VFs with the right number of queue pairs, rate limiters, DMA engines, buffer pools, TCAM entries, whatever, right? So these kind of things are what I'm talking about when I say granular hardware instances. Obviously, you need PCI hot plug capability so that once you made such a device of your liking, you should be able to show that device to the host. So there are open hardware specifications like virtio, NVMe, which are easier to deal with because they already define these granular resources. For instance, NVMe queue pairs, virtio has flow rules, vert queues. These are all predefined by the specifications, so you don't have to try to come up with new paradigms. So how do DPUs help in solving this problem? So as many of you already would have known, DPUs are a new class of all-in-one devices, accelerator devices adapted by cloud service providers. These are host-independent infrastructure devices. They can provide virtual network, virtual fabric storage, and other services to the host. They also carry a core complex with them, like for running control plane, for running orchestration, telemetry, and observability services. So how can DPUs help with composability? So first, taking the hardware part of it, obviously DPUs today are supporting NVMe, virtio, scalable functions, and so they can provide these more fine-grained resources like TCAM rules, crypto context, etc., to an orchestration framework for it to select and choose what it wants to inside a VF. DPUs provide device hot plug capabilities. DPUs also have started providing memory hard plug these days through CXL. Software-wise, once you have a hardware that is composable, you need software framework that can help any orchestrator to hit these management API endpoints to achieve the composition it's looking for. DPUs can run multiple frameworks. As of today, we have GPUs running Redfish, we have them running OPI, gRPC, and CDI, DRA, which is vendor specific. So inside a composable DPU, so this is an example of a composable DPU. A Marvell Octeon DPU is being shown here. So what we have done when we wanted to make these DPUs composable are we looked at what are the hardware units that are atomic and that can be assigned to VFs and PFs to make higher order devices. So we looked at, we call them local functions because every other names are taken, obviously. So these local functions are like similar to PCI class devices. You can have TCAM filter local function, QPair local function, crypto local function, DMA engine local function, and such. And these local functions can now be assigned to a PF or a VF or a SF, and you can combine these in the right quantities for your PF or VF depending on the load, workload you want to run for that tenant or container or VM. For example, here we show on the left bottom, there are two composed VFs. One is an NVMe VF and a NIC VF. You can see the NVMe VF is composed of a QPair VF, a crypto LF for NVMe encryption, and a DMA LF. Similarly, a NIC VF has crypto LF, a NetQPair LF, an MCAM LF, and a DMA LF. So these are the ways in which you can collect these LFs together and make them into higher order devices. So now coming to the software part of it, the orchestration frameworks. We have a multitude of frameworks. Redfish was an obvious API to start with. We do have challenges here because fine-grained resources are often vendor dependent. Every vendor has their own way of doing their hardware, so getting a common object models across these vendors, finding common object model is difficult. Open hardware specifications obviously are easy to deal with. They already define these subatomic or atomic resources like NVMe, QPairs, net flow filters, queues, whatever. So we have multiple frameworks in this area. OPI, Open Programmable Infrastructure. The booth is in the expo hall by the ARM booth. You can go check out. The OPI group is making progress in this area to make a uniform API that all DPUs can support. CDI DRA is obviously, as stated, a vendor-specific resource management that can be used in the Kubernetes environment. So here we show a Redfish composable provisioning sequence. So assuming that the DPU has a BMC that runs a Redfish endpoint service, it's also assumed that the DPU can be powered on independently of the host through aux power. Initially, the composability service or the orchestrator queries the DPU about what it has got in its resource list. And then once the resource list is returned, the orchestrator can then go ahead and compose a PF of its choice, and then create a PF and continue to do that as long as many as PFs as it wants to create. And then the host is powered on, and the host will see the PFs that the orchestrator wants the host to see with the right capabilities and capacities. And this is another example of storage composability using OPI API. So OPI group has defined storage APIs for front end, middle end, and back end for NVMe device composition. Here, the DPU is offloading a NVMe over fabric. So initially, the orchestrator has to create a remote NVMe controller and connect the local NVMe to the remote NVMe, and then it creates a local NVMe controller where you can see that you can provide while calling the create NVMe controller API, you can provide max queue pairs, max namespaces, and such, and all the composability parameters you want before making the NVMe PF. Once this NVMe PF is created, the orchestrator sends a command to hot plug the NVMe PF to the host, and the host can then use the NVMe PF as it has been composed. And now this is an example using virtio. So virtio community recently approved the CRUD API for virtio. So this is virtio follows a same sequence. You can assign virtio devices and the vert queues and flow filters to a virtio device before you can create a virtio device and assign it to a VM. So industry efforts, as said, we have Redfish, we have virtio, we have OPI API group, multiple groups working on this. What we are looking for is where does this fit in the OCP project umbrellas. We have OCP accelerator infrastructure, there is a NIC sub-project, there is OCP CMS already involved in composable memory, so we are trying to find out where this fits in the OCP umbrella of things. And again, call to action. Obviously, standardizing granular hardware is what is